Good morning, everyone. Welcome to day one of distance learning. Hopefully this will only be a week long. We'll see each other soon. I've got a warm-up for you to try. Go ahead and pause the video and press play when you're ready. Okay, so we got to find the area of the shaded region. Notice it's bounded by the function, the x-axis, and then the two vertical lines at x equals 2 and x equals 4. Those are all key components today that with the new idea we're going to be introducing. But we can approach this just as a geometric problem from geometry. Go ahead and find the area of the shaded figure. Well, it's a trapezoid. Remember your formula for area of a trapezoid, 1/2 base 1 plus base 2 times the height. Well, here your base 1 and base 2 are the vertical lines, and then the height is actually going to be what we're going to call the width between those two vertical pieces. And to find that, you can take the 4 minus the 2, or you have a height of 2. So plugging in what we know, base 1 is 2, base 2 is 4. We have a height of 2. Go ahead and multiply that out, and you'll end up with 6 times 2 is 12. Half of 12 gives me 6 units squared. Okay, next thing we're going to look at is, well, quote for the day. With distance learning here, I want you to know that we're going to do our very best, and I'm counting on you, counting on me. I'm actually also counting on you to do your very best. You know what it takes to be an active learner when we're in distance learning, so I'm hoping you're fully engaged, doing your best to watch all the videos, asking questions when you have questions, and making sure you're doing all of the work on your own. If you are working with somebody, you're productively learning, working off one another to help improve each other's learning. All right, so we're going to look at section 6.2 and 6.11, day 1. It's called the area problem, and it's kind of our general approach for the next big idea in calculus. The area problem is kind of defined here. Let's say we have a given function f. So that's the blue curve here. And it's defined by a non-negative value. So all these values are above the x-axis on the closed interval from a to b. What is the area of the region bounded by the graph of f, the x-axis, and then the vertical lines a and b? So same thing we just did, except for the difference here is this is not a friendly trapezoid. And actually we can't calculate this area using regular geometry. Even if we try to break this up in rectangles, you can see I would have a little bit of an overestimation on this part. Here I have an underestimation, so I wouldn't get the exact area of the function or the value under the curve, but I could get close. This would be a way to approximate the area under the function. All right, so let's look at this. We're going to go through a couple of different ways and introduce something called the Riemann Sum. We're going to look at about 4 different graphs, 4 different ways to approach this problem. It's just the function of a parabola, and we're going to go from the points 0, 1, 2, and 3. And so if I want to approximate the area is going to be, and actually we're going to introduce a new symbol right here. We'll explain this a little bit later on in the video. But remember, f of x can also be called y. So I'm looking for the area underneath the function between 0 and 3. Notice that's my starting interval to the ending interval. So what we're going to do is we're going to actually define this by looking at something we do know. We know rectangles. So I'm going to look at a rectangle based off of the right endpoints. So if I look at the points here at the outputs at 1, 2, and 3. If I draw a line here, pretend it's a nice straight line, what I can do is I can actually use this rectangle formed between 0 and 1. I can use the rectangle formed between 1 and 2. And then I can use the rectangle formed between 2 and 3. And notice if I find the area underneath that curve, that's the sum of those 3 rectangles added together. So our job is to use the right endpoints of each strip to find the height of each rectangle. And that's what we're going to do here. You'll notice I did some work already. So if I want to find the height of each rectangle, that's based off of the right endpoint of each rectangle. So see here I have the right endpoint for each rectangle. What I need to do is I need to figure out the output. So what happens when x is 1? If I plug 1 into the function, you can see I get 3 as an output. And then I have to find the height at 2. So plug 2 in for x, you get the output, and do the same thing at 3. And you can double check those outputs there. So what do we need to do? We need to find the right sum, which we're going to call r of n. This little subscript, n is the number of strips or the number of rectangles needed. So if I want to find R3, that's the right Riemann sum, what we need to do is we need to take and find the area of each rectangle. Well, what is the area of the rectangle? It's the height times the width. And the height is f sub 1, which we saw was 3. The times the width. Notice the width is the difference between your points. Well, 1 minus 0. And then do the same thing for the second rectangle. Its height is f of 2, which is 5. And then the width is 2 minus 1, or a length of 1. And rectangle 3 is the height, f of 3, which is 9. And then times the width, 3 minus 2 is 1. So you can actually plug those in. F of 1 is 3. 3 times 1 gives me an area of 3 for the small rectangle between 1 and 0. F of 2 is 5. 5 times 1 is 5. And then f of 3 is 9. And since they all have the same width, the width is always 1. So then I'll add those up and I'll get an area of 17 units. Now keep in mind this is an estimate. And you can tell based off of your drawing here, is this graph going to be an over or an underestimate? And you're thinking right now, you see all this overage. We actually counted extra more than we needed to. And the reason why we justify this as an overage, it is an overage because the function itself is increasing and we are doing the right endpoints. So anytime you have an increasing function and you're doing the right endpoints, it will be an overestimation. And I should probably write there it's increasing because we're doing the right Riemann sum. All right, there, I fixed it. So full justification, overestimation, because f of x is increasing and we are taking the right Riemann sum. So what we're going to do next is now we're going to try it with the left-hand side. But notice if I use the left-hand side, all of a sudden my rectangles become a little bit different. So we'll go ahead and try that in a second. So we are going to try the left Riemann sum right now. And notice a couple of things changed. All of a sudden I'm going to start with the left endpoint now, and I'm going to make my rectangle. And since the that's a positive 3. Since the left endpoint actually is the same here, both of these rectangles are going to be equal. And then I'm going to use point 2 to make the next Riemann sum. You can see each one of these rectangles, we are using the left endpoint to determine the height. So use left endpoint for each strip's height. We're going to call it L of n, where n is the number of strips. And same thing, we're going to set up L of 3 because I have 3 rectangles here. And we have to use the outputs f of 0. So where is f of 0? F of 0 is, right here on the left endpoint. Follow that up, we went up 3. So this answer is 3. The difference between the outputs 1 and 0 is the width. That hasn't changed. The second rectangle, we're going to use f of 1 because that is the left endpoint of this rectangle and its output is 3. And then for the third rectangle, we're going to use f of 2, which is 5. And then the difference between the width for each one is a difference of 1. And you can see that its area is 3 times 1 plus 3 times 1 plus 5. Notice both of those rectangles are the same. So they both have 3 plus 3 plus 5 is 6. And you'll see that this is an underestimate. Notice if we were to actually fill in the area that we found, our answer would not be enough to get close to the total area So this would be an underestimate. Why is it an underestimate? Because we're doing the left Riemann sum, and the function is increasing. So I just updated my justification. The function is increasing, f of x is increasing, and we are taking the left Riemann sum. Therefore, our answer will be an underestimation when we approximate the area under the curve. So that's the difference between the left and the right endpoints, and how you can estimate the area of underneath each curve. So what if I give you a new function, and this time we want to find the midpoint. So not the left or the right, but we want to use the midpoint outputs. This graph is actually wrong. I'll fix it. So for the midpoint Riemann sum, we're not going to use the left endpoint or the right endpoint. We're actually going to use the point that's right in the middle of your interval. So if I go from 0 to 1, then the midpoint would be right here at 0.5. So we're going to create a rectangle right there at 0.5, and I have to find the area of that rectangle. And then I'm going to use the midpoint between the second interval, so the midpoint between 1 and 2 is 1.5. And if I go straight across at 1.5, you can see I create a new rectangle. And then finally at 2.5, we'll create the third rectangle, and that's how we'll find our height. Well, to find the height, we have to figure out what is the output. Right? So I'm going to put 0.5 into the function for x, and we're going to find the output for each one. You can go ahead and do that now. All right, so I took 0.5, plugged it in, and I got the output. I took 1.5, plugged it in, and got its output, and I plugged in 2.5 and found its output. So now we have to find the area of each rectangle. Well, the area of the rectangle is the height times the width. So the f of 0.5 times 1 minus 0. And then f of 1 is the height, that's the output, 2 minus 1, and 2.5 times 3 minus 2. So if we use those outputs that we calculated, 2.75, 3.75, and 6.75, the width for each interval, because they're equally spaced, is 1. So then the total sum is 13.25. Remember, we're going to introduce this notation a little bit, but what did we do? We estimated the area under the curve by finding the integral from 0 to 3, that's the start to the end, using the midpoint Riemann sum, and got 13.25. Now, with this one, it kind of looks like it's an underestimation because the parts that we did not account for look to be a little bit larger than the ones that we had over. But this one we can't really be sure, so we don't fully justify if it's an over or an underestimation if you're using the midpoint Riemann sum. All right, let's look at our last item here. So what happens if I decide just to connect the left and the right endpoint? That's going to create a trapezoid. I know this looks like a rectangle, but we can treat it as a trapezoid. And you can see each shape is a trapezoid, just like you found the area of in the warm-up. So what we're going to do is we're going to set up the T3. I've got 3 trapezoids. Trapezoid 1 is 1/2 base 1 plus base 2 times the height. So let's look at that. Base 1, remember base 1 is the height. So that's going to be f of 0 or 3. And base 2 of the first trapezoid is f of 1, which is also 3. And then the height is, remember, height doesn't mean how tall it is. Height is the distance between the bases from 1 to 0. For the second trapezoid, I've got base 1 plus base 2, so f of 1 plus f of 2. And then the height is the difference between the interval 2 to 1. And the third trapezoid, we've got f of 2 plus f of 3, with its height being the distance between the bases. So if I actually evaluate that, f of 0 plus f of 1, 3 plus 3 is 6, times 1 cut in half is 3, excuse me, and f of 1 plus f of 2, 3 plus 5 is 8, half of 8 is 4, times 1, and f of 2 plus f of 3, 5 plus 9 is 14, cut in half is 7, And when I add that up, the area underneath the curve is 14 units squared. And then remember, we could write that with our new integral notation. From 0 to 3, the area under the curve is approximately 14. Notice I wrote f of x here, but we could also write the function itself in replace of f of x. And then if you look at it, the idea here, this is an overestimate, and when we do estimations for trapezoids, we actually look at the concavity. So this is an overestimate for the area because f of x is concave up, and we are using the trapezoidal sum. If it was concave down, and you created the trapezoids, you would see that there would be area above the curve that we didn't calculate, so that would be an underestimate. All right, let's actually look at these now. Oops, wrong one. And give you a chance to just recap what we did. Riemann sums formed using the left endpoints are called left Riemann sums. Ones using the midpoint are midpoint Riemann sums. And then the the Riemann sums using the right endpoints are called the right Riemann sums. When you connect the left and the right, you get trapezoidal sums. So, really quick, if you'd like, you can read more about this Riemann guy we've been talking about. Here's kind of his mathematician piece. The part I wanted to show you is if I want to estimate the area under the curve, what if I start with just a couple of rectangles? You can see there's definitely an overestimation here because it's an increasing function and we are doing the right Riemann sum. So how could I get more accurate? Well, what if I make more smaller intervals, which means more and more rectangles? The more rectangles I create, the more or the closer I will get to the actual area under the curve. And that was his conjecture, is that by actually creating an infinite amount of rectangles or trapezoids, you could find the exact area under the curve. So, just really quick, we talked about overestimation, excuse me, overestimation and underestimation. We can improve the approximation. So here, if I wanted to find the area under the curve and I had two rectangles, you can see we have an underestimation. Well, if I created more intervals, which means more rectangles, that error gets smaller and smaller and smaller. So by taking 8 intervals, I would be more precise than if I did 2 or 4. All right, so let's actually make a connection here. This is the part you definitely want to write down right now. It's called the definite integral. It's the signed area. When we say signed area, that means area being positive or negative between any curve and the x-axis on an interval. So here's this picture. If I go from A to B and I look at the area under a curve of f of x, that is going to be represented by our new notation. Now, I will share this. This is called the Riemann Sum notation. We're not going to do a lot with this, much at all actually, but it ties in the idea of limits, and it's just saying what happens if you take the amount of rectangles from 1 to n. So if I did one rectangle, I could estimate the area. But if I did an infinite amount of rectangles, if n went to infinity, then I could get the actual total area under the curve. And the notation is just f of x of I, where I is the amount of rectangles. That's going to represent your output, which is your height. And then the change in x is your width. So you don't really have to worry too much about that, but what that leads us to is this idea of our new notation called an integral. So I'll give you a second to write this down. You can hit pause, and when you're ready, we'll move on. All right, if you didn't title it the definite integral, please do. I kind of threw that back in down here. But that's going to be the work. We're actually going to spend basically the rest of calculus working with this concept of the definite integral. We'll actually get to an indefinite integral where we don't have bounds from a to b, but that'll come up later on. All right, our goal now is to use these ideas of left, right, midpoint, and trapezoidal sums to calculate the area underneath a curve. So you can go ahead and hit pause, try this if you'd like. We'll go over it in a second. An example, an object moves with a velocity v of t given in the table. So Notice I have intervals. This is basically the same thing as a graph. If you wanted to, you could graph this and get your function's curve. But we want to find the Riemann sum for v of t on the interval from 1 to 8. What are the units for the Riemann sum? Interpret the Riemann sum in the context of this problem. We're going to actually do the right Riemann sum. That should be indicated, and it will when you work through it. So try this one. We'll come back and go over it in a second. All right, let's take a look here. So what can you do? Well, to find the right Riemann sum, you can actually divide this up and think of these as being rectangles. You have 1, 2, 3, 4. Now notice right away, see how the intervals are not the same? The distance from 1 to 2.5 is not the same as the distance from 5 to 8. So our widths, or excuse me, the height of our rectangle is going to change. Find the Riemann sum. So what we're going to do is we're going to find the right Riemann sum. I'll have 4 rectangles. And then we're going to take the velocity at 2.5. So that will be the height. And then the width is going to be the difference of the interval, 2.5 minus 1. All right, so that's my first rectangle. My second rectangle is going to be the height at v of 3. Notice that's the right-hand side, v of 3. And then the difference between the intervals from 3 to 2.5 is the width. And then v of 5 is the height of this rectangle, and its width is 2, the difference from 5 to 3. And then the last rectangle has a right endpoint. We're using the right endpoint. That's v of 8, and then 8 minus 5 for the interval. So if I actually calculate those, v of 2.5 is 0 times 1.5. V of 3 is negative 4 times the difference between these two, which is 0.5. V of 3 is negative 4. Oh, sorry, I already did that one. V of 5 is 2, and the difference between 3 and 5 is 2, plus v of 8 is 5, and the difference is 3. So when we calculated that all out, I should get 17. What are the units? Now notice what we're doing. We're taking the output, which is meters per second, times the time, which is seconds. Well, the meters times the seconds times meters per second, they're going to reduce out. If we were to write that out, meters per second times seconds, the seconds go away, and you're left with 17 meters. So what does that mean? That means that the area under the curve, or in this case, the distance traveled from the first 1 to 8 seconds, or over 7 seconds, we traveled an approximate 17 meters. All right, so we just interpret it in the context of this problem. Let's look at another one here. Go ahead and try this. All right, let's go over this. So a couple things you need to look at. We have the function 2 to the power of x. Now that's our doubling function. If you think of it, it's just going to be increasing. It's going to double its amount each period. And we have to find the area under the curve using the right Riemann approximation. So I think about that. If I'm going to draw right rectangles, I'm going to use the right endpoint. First thing we need to do is figure out the 5 equal length subintervals. So how do we do that? Well, the first thing we're going to do is start here, is to find the interval width. If you want to write this down, or you can just use your intuition, if I start at 3 and I end at 5.5, I'm going to take that and divide it by the number of rectangles that I need, which is 5. So the difference of the two, start or end minus start, 5.5 minus 3 is 2.5. Divide that by 5, you get 0.5. Each interval width is going to be a 0.5 increment. Well, then what you're going to do, and you can see I already did that, is you need a table. You're going to need those outputs. So what I did was I created a table. I used my calculator. If you just type this into y equals into your calculator and then do table set, remember to change your table set. You go second window, and instead of going up by 1, you can change it to go up by 0.5 each time. We talked about that in class a while back. But then think of this, here's your rectangles. Right? If I draw my first rectangle, I want to use the right end point, so I'm going to use 11.314 as the height, and then the width is going to be the difference of the two, so 3.5 minus 3, which is 0.5. So I kind of set that up here. My writing is not very straight, but here's my first rectangle. My height is the output at 3.5. My width is the difference between 3.5 and 3. Well, notice every width is going to be 0.5, so I really didn't need to set all of that up. I could have just said 0.5. So I'm going to take the output times 0.5 for the first rectangle, and then my next rectangle, I'm going to go, if it was a little higher, here's my second rectangle. I'm going to use the output of 16 and multiply it by the width of 0.5, so 16 times 0.5. And then the next rectangle will come over here, and I'll use its height times my width, so 22.627 times 0.5. And then I'll do the next one at 32, and the last one at 45.255. Notice how we're not using the first given output. You don't use that when you're using the right rectangular approximation. If I was using the left one, I would use it, and I would ignore the last one. So then you multiply those together, add them up, and you will get your area underneath the curve is 63.598. Notice that's R5, the right Riemann sum approximation, or we could write it with our new integral notation from 3 to 8. My function is 2x, the change in dx, excuse me, dx with the sum of 63.598. And that is an overestimation. How do I know that? Because my function 2x is increasing from 3 to 5.5. So therefore, because it's an increasing function, we're using the right Riemann sum, it's an overestimation. All right, homework tonight, Delta Math 6.2 Day 1. Remember, there are the help videos embedded within. So if you need a little more structure on how to do a problem, you can watch how they do it, or you could rewatch this video. Good luck. We'll see you tomorrow.